Hey everyone, so welcome to this code walkthrough, which is part 2 for the MDS Locker internals. Part 1 for this was done a while back, somewhere in maybe July or August. So yeah, so we have some topics that we kind of left out because the Locker is a very big topic and it's hard to cover it in one code walkthrough. So we'll probably have one more of these to cover much more. So before I start with before I start with the current follow through of the last walkthrough, we'll quickly skim over what we discussed last walkthrough for this, since it's been quite some time and it's easy to forget some of the details. And Locker involves knowing quite a lot of details. Otherwise the understanding going forward is a bit hard. So I wrote this document down. This basically will end up as a pull request maybe in tomorrow or the day after. For documenting the Locker internals for MDS Locker implementation and design. Whoever I would love to have eyes on it, recommendations, changes, so that we start documenting these things. Part of the reason for doing this is much of the code regarding this is pretty old. It dates back to, some of the source code dates back to 2009. That's a good 11 years, 12 years, and has probably never been touched post that, or maybe just few changes here and there, and that too pretty minimal. So the code design is still how it used to be a while back. And it obviously makes sense to document this so that new joinees and people from the community can get themselves up to speed to the design, which is a much complex design, and hopefully it helps everyone. Okay, so quickly skimming through what we learned last in the last walkthrough for Locker. Why we use logs? Well, we all know that, right? Basically, everyone uses logs is to protect some state of data. In this case, these are various metadata pieces in the inodes and the D entry. The way MDS does it is, instead of having a big gigantic log for each inode, well, MDS has like MDS log, we all know that. But that's the entry point log, right? But once it enters there, there are different logs for different pieces of metadata in an inode and a D entry, and MDS uses different kinds of logs. So you'll see that different classes of logs, since different metadata in the inode and the D entry have different behavior in various situations. So what happens is, there is some metadata for an inode. Say we take the mode, access permissions, node, UID, and the GID. There's hardly any, there's hardly any workload that does, parallel, concurrent updations to the UID or the GID. Or maybe there's a reader that is looping through the UID and GID, checking it again and again, and there's a update client that sets it, and that is setting it again and again. So it's possible, but it's very there's no real world use case for this. So the Locker is optimized to do all to satisfy all these requirements in an optimal fashion. In the sense, Locker will treat things like UID, GID, and a bunch of other metadata as only allow read log and exclusive logs, which is like many clients can read congruently, which is fine. But when some client wants to update it, takes an exclusive log. So all the read logs are now all the caps from the reader clients are now revoked. While there are some other types of metadata that need shared read and shared write. Typically in the MDS, you'll think this for the recursive statistics information and the dir factory. So very very quickly, MDS, we all know It tracks a bunch of heat maps for each particular inodes and the entries, for inodes rather. And then when the heat or the excess frequency for that particular node, let's call it node, hits a threshold, the MDS thinks, okay, this has now been excess frequently. Let's go and split this directory. So there's the dynamic subtree partitioning. So when it does it, it splits the directory into multiple shards, and then if you have if a setup is running multiple active MDSs, some of these shards can be migrated to some other MDS so that client workloads are now balanced. So for this kind of scenarios, the MDS allows shared read and shared write. How it allows shared write is for a particular directory node, you can have a client creating some files in this directory, which is mapped to say MDS rank 0, and then a shard which is mapped to MDS rank 1. Some other clients can be creating directories in that. So the recursive stats and the refractory are, they can be shared read and shared write. So the MDS allows that. So this particular log class is now optimized for this particular kind of metadata. So we'll see how MDS splits this into log types and log classes. Okay, log types. So as I said, MDS defines a handful of log types associated with different metadata for an inode or D entry. So instead of having one big log for an inode or a D entry, it kind of splits it into splits the metadata, or rather groups the metadata into similarly excess configuration types. In the sense, so we know that like auth, if you see this cephlog IAuth, this protects the mode, UID, GID, and C time in particular. So these are grouped into IAuth. So whenever you're taking a read log, or say a read log, it's safe to read only these 3 or 4 metadata pieces. If you have taken, if you have acquired the iXATA log, it's safe to read the XATAs and the C time. And similarly for snaps and the sol. So if you see, we have like around 12 to 13 types, and each type covers a particular piece of the metadata in that inode and the entry. So these are log types. Quickly covering, this is like a split. These are types. These are log types that protect a particular piece of information in the inode or the D entry. Now the interesting part comes as log classes. Log classes define locking behavior for the associated log type, which is necessary for handling distributed logs. So MDS, because we can have multiple active MDSs in a setup, and clients can be talking to one or more than one MDSs, even for the same inode. We need a distributed lock mechanism, for safety, for access. So how this log classes work is, MDS defines 3 log classes, or rather 4, but majorly 3. One is the local lock. The local lock is used for data that doesn't require distributed locking. So if you're trying to increment the inode version or the D-entry version, you really don't need the distributed lock. All you need to be sure is you're in the authoritative node for that particular inode. And then you can take this lock. It's like it's a version lock. They are just counters. You take this lock, increment the version, and you're done. The other lock class is simple lock. This is the base class implementation for distributed lock. It defines much of the locking rules locking rules to implement distributed locking. Simple lock, which is what we'll be covering today majorly. Later we'll see scatter lock and file lock. So simple lock is used for data that requires shared read and mutually exclusive writes. As I mentioned earlier, things like the mode UID GID, things like the link count, XATAs, snapshot list, and all. They require shared read and mutually exclusive writes because of the access patterns, right? I mean, there's hardly any access pattern that does parallel reads and parallel writes for UID GID, but such a pattern is pretty common for
for different files in a directory. So we have that's how we differentiate. The MDS differentiates different access types. So as I said, simple lock is the base class that defines rules for distributed locking, and many metadata pieces are simple lock. I think majorly it's simple lock, and probably just a couple, maybe 2 or 3 are like scatter locks and file locks. So we'll cover simple lock in this talk. Just to cover scatter lock. So this is used for data that requires shared read and shared write. So as I said, things like recursive stats and refractory and like um, those kind of things, they require shared read and shared write. So the MDS also can kind of delegate some authority to other MDS replicas. So if a particular inode is getting really hot, access is getting really, it's being accessed by a client a lot. So the MDS can now, create a replica for that particular inode and then distribute that replica copies among other active MDSs, which again can generate read capabilities for clients. So that requires, shared read and shared write kind of access mechanism. There's where scatter lock comes into picture. And then in addition to this, there is a file lock, which is like a special case of scatter lock. Again, that's for shared read and shared write. But additionally with that, it also protects pieces of metadata that require shared read and exclusive write. Things like M time, things like the size. That requires most of it requires shared read and shared write, but these additional metadata pieces require shared read but exclusive writes. So there's where file lock comes into picture. Now, how these lock types are classified. Okay. So as I said, simple lock, we have this, and I'll quickly show the code where all this is done. Do you still see the my window? Just flip things around.
I can see it.
So all this is we'll come to this in a bit, but a small note is most of these log types, they're like these 13 log types are mostly for the CI node structure. There's only like a couple of them for the entry structure. So we'll majorly just concentrate up with I nodes in this. So if you go to the CI node source, you'll see. I think I just missed it. So it defines a bunch of log types, and then it defines which are simple logs, which are local logs, and which are scatter logs. So I just kind of rearrange this for brevity. Simple log, majorly we have simple log, like the auth, like ModuID, JD, link count, etc., snap, layouts, file logs. All these require just simple logs. Then we have scatter logs, the complex one. That is for the INEST and IDFT, which is nothing but the nested info, the recursive stats, and DFT is the refractory. So these two are scatter logs. And I explained why do we need scatter log for these, right? Because we need shared read and shared write kind of scenario. File log, again, this is kind of a special case for scatter log, and this is for the iFile type. Again, iFile, it protects M time, A time, size, truncate, a couple of things for handling truncates, client pages, and then inline data. And then we have the more simplistic type of log, which is like local log. As you can see, these are all version logs. I version is for the inode version, D version is for the D-entry version. These are just local. These are not distributed logs. These are always taken by the auth MDS for that particular inode. Any confusion up till here? Anything, any questions? Feel free to interrupt me in between or just put them in the chat. Okay. So now for each of these log types, MDS allows you to acquire these logs in 3 modes. Normally would have seen, we have just typical, if you use a pthread log, you can, or a normal log, mutex, you can use it in read mode.
can either use it as a plain mutex, which is like somebody has taken a lock, irrespective of whether it does a read or write operation, takes the lock, so that guarantees mutual exclusivity, and then modifies the data in question, and then comes out and then unlocks. There is another, so this can be taken forward with read likes and reader locks, in which multiple readers are allowed to access a particular data structure. So you take read logs, you can have concurrently three, four, entities reading under that read log. But once you take a write log, no readers or writers are allowed. So that's the exclusivity. MDS, however, defines this in three modes. One is the RD lock, which is the shared read lock, the WR lock, which is the shared write lock. Again, so there's not the exclusive write lock. WR lock is a shared write lock, and the exclusive lock is called X lock. So RD lock and X lock are pretty self-explanatory. We all know that. Shared read, shared write, we just discussed. WR lock is special since it allows congruent writers. And the thing is, WR lock is only valid for the lock class type scatter and file lock. So you won't see the WR lock being taken for simple locks. Yeah, I mean, IAuth or iLink types, they only support read locks or exclusive locks. Even when we go to the state machine transitions, we'll see, it's only the read lock or the exclusive lock that makes sense for that particular lock class. So WR lock only makes sense for the scatter lock and the file lock, and we'll see the state machines. And why I kind of explained this, WR lock, allows multiple writers at the same time. Again, when a large directory is kind of split into shards or nodes, each of these shards can be kind of, delegated to a particular active MDS. And when new files are created under these fragments, MDS needs to account for the recursive stats. So each of these two shards, recursive stats for these two shards are kind of accounted independently by those MDSs. This is done on the write lock, and if a client wants to read these statistics, a read lock is taken. When the read lock is taken, what happens is there is a gathering mechanism, or so what happens is the MDS kind of gathers all this accounting to the auth MDS, and then the read lock is guaranteed. So scatter lock and file lock they have the scatter gather mechanism. Scatter is when you take a write lock and the IOs are scattered, in the sense, different clients can operate on these different shards independently, scattered. And when the time comes when you have to kind of do an aggregation, you take a read lock in most cases, and the statistics are now aggregated in the auth MDS, and the read lock is guaranteed, and then the correct stats are propagated to the client. There's this special remote WR lock that is only valid for cases where you do a rename, where the destination D entry is actually on a different MDS than the current one. So the source D entry might be on MDS rank 0, but you're trying to rename it to D entry which lies on MDS rank 1. So the MDS 0 will send a lock message to MDS rank 1 so that is not mentioned in all those inter MDS lock transitions are not covered in this talk. We'll cover this in the next talk, but just touching upon it, there's an inter MDS lock message that is sent, and so the MDS 0 can tell MDS 1 to kind of write lock. So that operation is called the remote WR lock. Okay, now we have lock states and lock state machines. So these are the most interesting things, and we'll just stick to simple lock for this. We'll touch very briefly in scatter lock and file lock so that we get a feel of the state machines and how the state machines differ between simple lock, scatter lock, and file lock. But we won't go into more detail because it's very confusing. So you need to first understand how simple lock works, get used to it. Maybe try out a few things on your own, and once you have like a good understanding of simple lock, we'll see how scatter lock works. Okay, so MDS defined various lock states. So we have a whole bunch of states. The good thing is for a particular lock class, we don't have to worry about all the states. So we have around, I think, 35 to 38 states. Total number of states, but for simple lock, you might just touch a handful of them.
A scatter lock and file lock are much more complex, and they touch a much more bunch of states. So we'll see where all this lives. Go to MDS logs.h. So these are the log states. We have a whole bunch of them. It's obvious to say it's like not documented at all. So the only way to do it is to go through the code, do some experiment, and see what each of these log states mean. As I said, simple log, you don't have to worry about much of the states. We'll go to the state machine and see, it's just a subset of these log state that simple log is concerned for. Okay. Okay. So one thing which is very important here is these log states, what you saw, the log underscore blah and log underscore blah underscore blah. These are not log themselves. It's pretty confusing because by naming you kind of expect them to be logs, but these are not logs. These actually control if a log is allowed to be taken. So each of these states depict if a particular type of log is allowed to be taken in that state. These are not logs themselves. And if you see, there are two kinds of naming convention here. If you paid attention closely, you'll see you had lock underscore a state, and then you have lock underscore blah, which is like state 1 and state 2. So the meaning for this is how these are defined is each state follows a naming convention, which is like lock underscore state name. So if you see here, the state is like sync. Here the state is like lock. Here the state is xlog. Here pre-xlog. Here the state is xlog. So lock underscore state name depicts that the current state is the leading name after the underscore. The other convention is lock underscore something underscore something. This is an intermediate state, which is also called as a transition state. So when the MDS wants to move from one state to another because a client is doing some operation, maybe it wants to take an exclusive log, it moves from one state to another, and we'll see why these intermediate states are required. But think of this as MDS needs to go from one state to another by visiting a bunch of intermediate states. So these intermediate states are named as, so if you want to go from state A to B, there's say one intermediate state. So you're in state A, lock A, say lock A, and you want to go to lock B, and there is one intermediate state. The intermediate state is named as lock underscore A underscore B. Okay, so if you see here, lock sync lock, this means the intermediate state is going from sync state to the lock state, and the intermediate state is lock sync lock state. That it is a bit confusing with all these lock naming carried around everywhere. I just hoped it was named something else. We could do that, but for now, just think of these as intermediate states going from state A to state B. Okay, I hope that's clear. If not, speak up please, and I can repeat that because that's critical in understanding the log state machine. Okay, I think we can go forward. So each of these states, we will not worry about intermediate states right now. We'll just quickly see what each of these states mean. The primary states. These are also called as stable states. By stable states, so if you see the logs.h, we'll see the state machine, but this is how the state machine entries look like. You have a next state which you want to, which the MDS says this is the next state we want to go. If the next state is 0, which means it's a stable state. Stable state means when an MDS is done transitioning from one state to another, when the request completes and everything is done, there's a tendency for the MDS to go into the stable state. So in the state machine, you will see, each of these entries have something called, if it does have another state, it says, this is the next state to go, or if it's 0, it's the stable state. And there's always a tendency to go towards stable state.
We have this lock sync state. The sync state says the meaning of sync state is anybody can read, but no one can write lock or exclusive lock. Um, if you are in like sync state for a particular lock type and you get a read lock, you don't have to transition between states. Since it says you can read lock uh, freely, and you're done acquiring the read lock. But if you want to write lock, then obviously because sync state doesn't allow you to take write or exclusive lock, you need to transition states, which means going into an intermediate state and then to another state. So next, lock is nobody can read lock, but only primary MDS can write lock or exclusive lock. So for simple lock, you mostly need to understand lock sync, lock, and lock X lock. Lock mix comes into picture when you're dealing with scatter locks and file locks. So a lock is, I mean, some client is already holding an exclusive lock. There are other bunch of states which are really not valid for simple locks, but most of them are really optimizations for locks, which needs to be, the understanding needs these form the basis of understanding the distributed lock behavior. There are other locks like locks XIN, and lock TSIN. They're kind of optimizations over the lock mix state. We'll cover those later. I'll most likely document them here so that wait for the next code walkthrough. But for this particular talk, we mostly need to worry about the lock sync, lock, and XLock state. So I did mention, intermediate states like, lock underscore from state to state. It denotes a transition of a lock from one state to another. Okay. Yeah, this is where it gets really interesting, where we see state machines and things like that. Okay, so when does the MDS, does all these state transitions? Transition of a lock from one state to another is mostly when a client does a request, when a client just, does an operation that reaches the MDS and the MDS feels that it needs to kind of now do all these lock changes. Or the other case is if the MDS, excuse me, or the other case is if the MDS has picked up a node from tree migration. Maybe because it thinks a balancer got invoked and then it needs to kind of migrate this particular subtree to another MDS. So, even in that case, it might, prompt a transition of logs. So we'll pick up a case here where, we'll deal with simple locks. We'll deal with the IOTH lock. IOTH is like, it protects the mode UID GID. So we'll pick up a case where one client is doing a read on the inode, on this particular inode metadata piece, which is the UID GID, say, and another client is concurrently doing an update of the UID and the GID. And we'll see how the lock MDS transitions the lock. So say the read, the client that is doing the read of the inode metadata piece, it probably did a couple of times, and then it got the UID GID, and so the client is still alive, which means it has the AS caps. So A is for auth and S is for shared. So I didn't cover more caps, the cap format in this particular talk. It's pretty well documented in one of the help documents that we have, or in the docs.ceph.com. So please go look it up there. So you can have like, for each particular cap type. So A is for auth, you can have either the shared cap or the exclusive cap. And because this particular client did a read, the MDS probably assigned a shared cap for it. So if it did a stat, trying to fetch the mode UID, since it already has the shared cap, there's no need to query the MDS, or the client can, satisfy that request from the from its local cache itself, which is the inode, cached inode.
So now when the other client does a set at a call to the MDS, the MDS, so we'll see this. Where did it do? So time to see some code. MDS server. From in the end, what happens is, when a client does this set at a call, it passes through a bunch of layers in the MDS, some sort of source classes, handle client set at a. So we reach set at a. So we reach this piece of code here. Now, depending on what flags have been passed, what kind of mask have been passed by the client, uh, you know, we add different locks. So for the simplistic case, we'll do here, obviously, kind of we are having these file lock and version logs. We'll not go into detail into this. We'll just be concerned about this case because we need to kind of understand how simple lock works, and then we can, add these complexity layers of what happens when a simple lock is taken and then a file lock is taken. So since we have, so the client probably passed, he's interested. That the client is interested in fetching the mode UID and the GID. So we did a statex, passed these flags down, and we came here, and this particular line got sufficiently valid, and then we added a xlock for the auth lock. So a little bit of information here is how the locker class is interfaced. The locker class, many of the APIs in the locker class accept something called as a lock op vector. So what you can do is one of the users of the locker class can pack in a bunch of different lock types in a vector, which is called the lock op vector, and then hand it over to the acquire locks API interface for the MDS to acquire the lock in an optimal fashion. So the lock op vector is nothing but, if you see in it's actually just a vector. It obviously some class typing around it, but in the end, it's like a vector of locks. So we can add different locks. You can add xlock for the auth lock. You can have xlock for file lock in this case, and you can have a write lock for the version lock. And then you call the acquire locks API, giving the current request and the lock of vector. And then, so what the acquire locks API does is it first, kind of rearranges the different locks in the lock of vector in a particular order. It always does that. So you can pack all these locks in any order, and the acquire locks interface will kind of reorder it. And then for each of the lock that we have placed, it will try to acquire the locks. Okay. So here we are mostly concerned about the xlock and the auth lock. So let's see. If you see locker, where locks. So we'll see here. So first, it does more than that actually. It first does it also auth pins the inode that are involved in the logs. So we'll skip that for now. Yeah, here is the sort and merge where it sorts the different logs in a particular order and probably merges it. Then again, it iterates over the pins. Grabs local auth pins. This is not of interest for this talk. In the end, we reach here. Is where we actually iterate to these ordered and merge lock of vectors, and then we try to acquire locks. And if you see, if a lock is of a particular type, not type, particular mode, do this, or if it's of write lock or remote lock mode, do this. If it's like else, the else case is like for if it's a read lock, do this. So it's pretty, 3 blocks that we have to be worried about. And it does this for each particular lock entry that we have put it in the lock that we entered in the lock of vector. So coming back, don't worry about the file lock and the version lock right now. Concentrate about the auth lock. So we said, the set data needs to modify the UID, GID, and the mode. So we need to take an exclusive lock for the auth lock. So what happens is we come here, we reach here.
And we'll go through the code in a little bit right now, but let's see what's actually happening under the hood. What happens is, so again, as I saw, as I said, we add this xlock. Now, the acquire logs thing, it goes to various branches, and in the end, what happens is it knows that this particular it knows that the lock that it needs to xlock is of a simple lock class type. So it goes and fetches it sees the simple lock state machine. So this is the simple lock state machine. Probably, does this look better? Anyone?
Yeah, looks good. Yeah, I can read it.
Okay. Yeah, I mean, it's not wrapped. It needs to be in a single line for, be really clear. Anyway, so this is the simple lock state machine. So how the state machine is written is, each of the entries follows this particular struct type. So if you see, you have next state, loaner, replica state, so that is followed here. Each of these entries follows the same order. So this is the stable state, this is the loaner, then it's the replica state, can read, can RD lock, can WR lock, and all these kind of things. So kind of depicted here, this is like RD lock, this is write lock, this is force write lock, this is I think loaner, and then this is X lock. Yep, lease. Sorry, not loaner. This is lease, and then these are X lock. And we'll come to these caps here, which are really interesting. So whenever you initialize a lock, the starting state is always lock sync. It's hard coded. The starting state is lock sync. Now what happens is, so the MDS wants to now, go from the lock sync state to the xlock state. Xlock state because we need to xlock that particular auth lock. We need to go from lock sync to xlock state. So the thing is, now we go into a bunch of intermediate states. Okay, so how it's done is, first, so if you see, I have detailed something here. So in the lock sync state, you can only read lock. If you see the state machine here, you can see that lock sync state, you can only read lock. Read lock, nobody can write lock, nobody can force write lock, and nobody can xlock. These definitions of any and exclusive are again mentioned in in the logs header file. So any is like anyone, auth or replica. Auth is like auth only. Is like the XCL is exclusive, is either the auth or the exclusive client. Request, we are not bothered about this right now. So log sync state is, nobody can write log or exclusive log, but you can only read log. The log state says, if you go back here, nobody can read log, but the primary and MDS can write log or exclusive log. Okay, so if you see, we need to kind of go from lock sync state to lock via to lock xlock via lock. So lock is it's a stable state because it's lock underscore state name, but again it's an intermediate state, kind of an intermediate state, and I'll explain why we choose why we go through various intermediate states. But for now, let's see here. So we need to go from lock sync to lock xlock via lock. So the way this is done is, so we need to go from sync to lock. So the next state that is chosen here is lock sync lock. So if you see lock sync lock, so we jump to this state. There's a concept of loaner which I'll explain. Not really required now. It's good to know, but not really a requirement to understand the state machine. This state says, lock sync lock says, you need to now go from lock sync to lock sync lock as the next intermediate state. This intermediate state has two purposes actually. So the first purpose is, in this state, if you see, it says no. for each particular intermediate state, only some types of caps are allowed to be taken by the client. So the log sync log state says that these are mentioned here. If you see these last four fields, which are nothing but the caps, the loaner caps, the xlogger caps, and the replica caps. Don't confuse. For now, for simplicity, just worry about these caps. It says, log sync state says, you can't have clients which have taken the shared log for this particular log type. So you can't have clients that have taken the AS log. So what happens is the MDS, when it reaches the log sync log state, it sends a revoke to clients which are having the odd shared caps, AS caps. And the other, requirement for having an intermediate state is when you have reached that intermediate state, it prevents further read logs to be taken. So when the MDS has reached log sync log state, it sends these revoke messages, cap revoke messages to clients. It's now in the sync log state, but if some other client comes in and tries to read log now, even that should be disallowed. So this intermediate state solves two purposes. One is to actually revoke conflicting caps from the client, and the other is to prevent further certain logs to be taken. And now what happens is once the client has replied to the cap revoke message, so we sent a cap revoke message like revoke the orchard caps. The client drops that particular cap and replies back. And next, what happens is we move from the log sync log state to lock log. So the next state, if you see here, is the lock log state. So once we move to the lock state, our end goal is to acquire the xlock, but we can't. So which means from lock we need to go to the xlock state. Again, how do we do that? We do that via going to an intermediate state, which is lock, and xlock. So we go to this state, do the same thing again. If there are like conflicting, caps that need to be revoked, we do that, and once that is done, we jump more states. Like from here, we jump to pre-xlock, and from pre-xlock, we finally go to the xlock state. So there's a lot of state hopping around here, but each of them have a meaning. So if you see here, what happened was I've taken this from the logs. Again, for for this case where where one client is trying to get an xlock and some of the clients have the auth shared caps, the MDS, the MDS sends a cap revoke message. So it says this particular client, it has these caps, so you can see the auth shared caps, but that is not allowed. So these are the only allowed caps we have. So we send these to the client. So the client drops the auth shared caps, replies back. So where is this done? CMDS .cc. So most of this starts with xlog start, since we are dealing with xlog start. There's lots of conditions here. We get to a point, where we do a simple lock because we are in like sync state, and that's a simple lock. So in simple lock, we see what's the current state. Initially we are trying to move from the sync state. So the next state is like lock sync lock. Once that is done, here is the thing that happens. So here the MDS finds out, that refers to the state machine. This is in C inode, by the way, C inode.cc. So if you see shoot caps need gather, you see it, refers to that particular state machine, and gives and gives back whether we need to kind of revoke certain caps or not, depending on these particular operations. So here we figure out that we really need to now issue or rather revoke caps, and issue caps is where we issue caps is where we loop through all the caps, and for that particular client we send a revoke message. So depending on many things, I'm not going to details of each of these, but you can easily find out that you have a bunch of caps that are allowed, and this particular client is holding those caps. Those are conflicting caps. So what you need to do is actually send a mClient caps message with the new set of caps. So the client gets this new set of caps, compares with its own set. It figures out that it needs to drop some caps, drops and replies back. So yeah, that's the crux of it actually. So once you have done, gone through a bunch of these states, each of these states have a certain, meaning. These are actually grouped. If you see, there is a grouping of states, and the MDS kind of does an automatic transition between these group states. So you can see, we went into lock, xlock, then pre-xlock, and from that, the final state is xlock. So a bit about the stable state is, as I said, MDS has a tendency to move towards stable states. These are when it completes an operation. So lock sync, lock, and lock exclusive are stable states. Xlock is not a stable state. The reason for that is, once the client has, the xlock is acquired, after the operation, we go into xlock done state. And depending on various other factors, depending on what other clients are requesting, we either jump to the sync state or one of the other states. That's an implementation detail. Design is, I'm not sure why was this taken, but the idea is, once the client has done an xlog, all these new changes, like if it has added a particular UID, that are sent to the other clients via the trace information. And most likely the clients, the other clients will probably be reading this information, and in that case, you need not jump into lock transition states again. For this case, what we saw is, once it has done with the xlock, it goes back to the lock sync state again. And when the other client does a read again, it does, because lock sync states, anyone can read lock. So at that point of time, it just, the lock acquiring is satisfied without going into these transition states. Yeah, again, so we go into these lock, xlock, then pre-xlock, and then finally to xlock state. So yeah, this was a simplistic case in the sense, we didn't have, most of the locks are like not allowed, and they had to drop the locks. But if you go to the complex ones like file lock, if you see the lock sync state here, you see the sync lock state here. It says, clients are okay to have the FC, which is like the file cache cap, and that is allowed. Anything else, if the client is holding like file shared caps, that will be revoked. But this lock, if one of the clients is holding a file cache, which is like the client can synchronously read from the OSDs and also cache those reads, so that is allowed. This happens when this is basically in the file lock case. So again, the lock state transition is same. We start with lock sync. We switch to lock sync lock. Again, we drop, try to revoke it. But during the revocation, we found that some of the clients are having file cache caps, and it is fine. So we don't revoke file caps. And again, we go through the same thing again. We enter lock. Enter lock state. Let's quickly see. Enter this lock state again. Again, a bunch of caps are allowed. It's okay to have for some of the clients to have these caps. So this is like the file cache and the FCB cap, cache and buffer. So those are not dropped. It's mostly an optimization. So for certain states, it's okay for the client to have certain caps, like there's the file lock. So it's okay for the for some of the clients, to have the FCB caps. Typically when this would happen with file lock is, when somebody is, when one of the clients is trying to read the M time, which is protected by the iFile type, and another client is trying to, kind of do a write which changes the M time. So in that case, some of the lock and some of the caps are allowed and safe to be held by the clients even in between the state transitions. There is this interesting uh, state called Exin, which is like mix, but the idea is, so if some of the clients, if one of the some clients have the FB caps, which is like they are buffering their writes. If those needs to be revoked, if the MDS revokes those caps, the client need to flush out those buffered data, dirty data to the OSDs. So there's this optimization where, for a case where one of the clients is doing a listing of directories and files and directories, and some of those files are being written by one of the other clients, and that client has a FB cap, a file buffer cap, so it's caching, it's buffering all these writes. If the MDS had to revoke the FB caps, the client has to flush out data again and again. When the other client is doing listing, if that is a contending cap, it needs to flush out the dirty data to disk, which is kind of expensive. If it has to do it again and again and again. So what the MDS does is it's an optimization where it figures that, okay, it's not really required to flush out the dirty buffer. So it enters this Xsin state where the client which is buffering the data, the writes, it can release its caps, which means the further writes will be stopped, but the dirty data won't be flushed to disk. So it's kind of an interruption to the write, and so that's an optimization. So the client having the FB caps, it doesn't have to kind of flush all the data to the OSDs. It can just stop writing, release the caps. Revoke or rather drop all these caps, and once it goes out of the Xin state to back to the mixed state, it tells the client to continue writing, and it proceeds as expected. So these are all these optimization states that the MDS has. There is also a tsync state, that is a temp sync state, which I have not figured out yet. But that's another state, intermediate state for optimization. So yeah, that's all I have for this talk. So yeah, we just covered simple lock here. In the next part 3 for locker, we'll go into much detail into the scatter lock and the file lock, and we'll pick up similar examples where one client is modifying an NM time and the other is doing a write, and we'll see how these state changes. Again, so most of the code is in locker.cc. The entry point for simple lock would be xlock start. So we have the start and end and finish routines. So these are called, start is called when you start to just starting to take that lock. Finish is done when they actually you're done locking. And a minor point is, if at some point of time you can't really take a lock for whatever reason, the MD request, the request from the client is actually put in a queue, and it waits for certain certain events to happen, which maybe some lock has been taken by some other client or something else. Once that event gets resolved, this particular MD request is again woken up, and it continues, and it starts again with starting to take the lock again. That's how it is.
And that's all I have for this talk. I'll put this document out as a PR maybe in a day or two, probably tomorrow. And good to have some documentation on the logging stuff. I'm ready to take any questions that you have. I'll stop to share my screen now.
So Venki, just to, to make sure that I followed parts of it. So initially you started off with server.cc code going through the metadata FOP, right? And you concentrated on the auth xlock, right? And the auth xlock is of type simple lock, and you went through the different transitions, specific transitions of that particular auth xlock. Is that correct?
Yep. So the lock type is called auth lock, not auth xlock.
Okay.
So we have a lock type and a lock mode. So you can take auth lock either in read lock or exclusive lock, because it's a simple lock type. And the simple lock class, you can add, so auth lock can either be acquired in read lock, RD lock, or exclusive lock.
Okay.
And yes, once that is done, we went into the locker class, acquire locks, where we see, the locks are rearranged and merged. And then for each particular lock type, the locker class consults the state machine and then follows the state.
Okay. And the different columns, can you bring up the state transitions for simple lock? There were different columns, right? R, RD, and I couldn't follow all those columns.
Yeah, hold on, let me share my screen again. You see all this? Is it visible?
Yeah.
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 So
talking about the columns on top, right? The column names are RP, RD, WR, FWR. So I guess those are the capabilities.
Yeah. So the way you read this is you go to actually you have to split your screen, and that is helpful. The way you do this is you go to the logs header and you see the SM state P structure. Each of these is actually mapped to each of these variables. If you see, the last four are caps, loaner, xlock, and replayer caps. So here, these are the last four. You have these can RD lock, can write lock, force, write lock, lease, and xlock. That is mapped to this RD lock, write lock, force, write lock, leases, and xlock. Yeah, that's how you read the state machine. Is that clear?
Yeah.
It takes some time to kind of map, but you have to look at each of these states more closely and map them back to that struct that I was talking about to see what each of these state means and what is allowed and what is not allowed. Like lock sync, as I said, it's pretty simple. You start with simple lock, and that's the most, other locks are pretty confusing. Just start with simple lock. Here you can see anybody can RD lock. Nobody can write lock or X lock. So 0 is like, where you see 0 is like that is not allowed. Any is like auth or replica, and if you see auth, that's only the authoritative MDS that's allowed to lock.
Yeah, makes sense.
Any other questions? I'll take that as a no. Thanks, guys. And yeah, please go and once I put the PR up, please make it will be good if we can put some comments on it. We need to really start documenting these internals for for the sake of it. Yep. Thanks, guys. Bye.
Thanks.